You're boarding a flight, you glance out the window at the wing, and there it is, that weird little fin curling upward at the tip, like the plane is trying to high-five the sky. You've seen it 100 times, but has anyone actually explained what it's for? Because the answer involves physics, money, and one of the most expensive problems in aviation, and it's way more interesting than it looks. The problem. To understand winglets, you first need to understand the enemy, drag. When a wing generates lift, it's basically creating a high-pressure zone below it and a low-pressure zone above. Air wants to move from high pressure to low. That's just physics. And at the wingtip, where there's nothing stopping it, that air curls around the edge and shoots upward. This creates a rotating spiral of air that trails behind every aircraft, called a wingtip vortex. You've seen these on foggy mornings at airports or behind crop dusters. They're beautiful. And they are absolutely brutal on fuel efficiency. These vortices drag against the plane. It's called induced drag, and it can account for up to 40% of total drag on a commercial aircraft in cruise. 40%. The engines are essentially fighting a whirlpool the plane is creating for itself. The solution. So, how do you fix it? The obvious answer is make the wings longer. A longer wing spreads the pressure difference over more span, which weakens those vortices. And it works. Longer wings are more efficient. But there's a problem. Airport gates are designed for specific wingspan limits. A Boeing 737 has to fit in the same gate at Lahore, London, and Los Angeles. You can't just keep stretching the wings. Enter the winglet. Instead of extending the wing outward, you bend it upward. Same aerodynamic benefit, breaking up those vortices, without violating the wingspan box. The winglet acts like a barrier that weakens the pressure differential at the tip. The vortex still forms, but it's smaller, weaker, and forms further out. Less drag, more efficient flight. The numbers. Now here's where it gets real. We're not talking about a minor improvement. Boeing's blended winglets on the 737 series reduce fuel burn by around 3 to 5%. That sounds small. But a 737 burns roughly 2,500 liters of fuel per hour. On a 5-hour flight, you're saving about 600 liters. Multiply that by hundreds of flights a day, across a fleet of dozens of aircraft for 365 days a year, you're looking at airlines saving hundreds of millions of dollars annually. That's why airlines were retrofitting old planes with winglets for years. The payback period was typically under 2 years. It's one of the most cost-effective upgrades in aviation history. The evolution. Winglets have evolved a lot since their first use in the 1970s. The early ones were simple vertical fins. Then came blended winglets, that smooth curve you see on most 737s. Then split scimitar winglets, which curve both up and down. Then the raked wingtip, no curl, just a longer angled extension, used on the 787 Dreamliner. The most advanced version today is probably the Boeing 777X's folding wingtip. The outer section literally folds up at the gate to fit gate limits, then unfolds before takeoff. It's a mechanical solution to a geometry problem, and it's wild to see in person. Airbus went a different route with the A320neo family. They use sharklets, their name for winglets. Same concept, slightly different geometry, same result, less fuel, lower emissions, more range. The physics. Wings generate lift through a pressure difference. Low pressure on top, high pressure on the bottom. At the wingtip, that pressure differential has nowhere to go. Air from the high pressure zone curls around the tip to the low pressure zone, forming a trailing vortex. This is called induced drag, and it's inherently tied to the act of generating lift. You can't completely eliminate it, but you can reduce it. Why not just longer wings? The straightforward solution is a longer wingspan. Spread the pressure differential over more area, and the tip vortex weakens. But wingspan is physically constrained by airport gate sizes, hangar dimensions, FAA regulations. A 777 already has a wingspan of 64 meters. You can't just keep making it wider. Winglets are essentially a workaround. They give you the aerodynamic benefit of extra wingspan, without the logistical cost of more horizontal span. The design evolution. Early winglets in the 1970s were crude, basically vertical fins. Modern designs like the Boeing 737 MAX split scimitar winglet or the Airbus A35 O's-raked wingtip are three-dimensional, twisted structures tuned specifically for each aircraft's flight envelope. They angle outward, sweep back, and curve because the optimal geometry at cruise altitude is completely different from what works at takeoff. The best designs today reclaim energy from the vortex and convert it into thrust. Whitcomb's insight was this: a small vertical surface at the wingtip could interrupt the vortex before it fully formed. The air trying to curl over the tip would instead push against the winglet, and if you angled that winglet correctly, that sideways push could be tilted forward. Wasted rotational energy converted into thrust. His wind tunnel tests at NASA Langley confirmed it worked. The problem was that nobody wanted to pay for it. Airlines weren't interested in the late 70s. Fuel was cheap, and retrofitting aircraft was expensive and complex. It took the oil crisis of the early 1980s, and then a persistent campaign by a few engineers to convince Boeing and Airbus that the math made sense. The first commercial winglets appeared on business jets. Then slowly, reluctantly, the big carriers came on board. So next time you're staring out a terminal window at that bent wingtip, you're looking at decades of aeronautical engineering, billions of dollars in savings, and one of the most elegant solutions in modern aviation. The plane isn't just flying, it's fighting its own wake, and the winglet is how it wins. That's it. 5 minutes. Now go look smarter than everyone else on your next flight.